Okay, this problem here is in a category of problems that involves two conservation laws. In this case, conservation of energy and conservation of translational momentum. There are no non-conservative forces in this problem, so we have conservation of mechanical energy in particular. So what we're looking at here is a cannon that is attached to a carriage. The weight of the cannon plus carriage is given as one object. So basically this whole object here has a particular weight. Okay, and then we have a ball that is going to be launched out of the cannon. Right, so we can draw that here. And that has an unknown mass. Okay, so the mass of the ball is unknown. M ball is our single unknown value that we're trying to find. We are told the spring constant of the spring. We're told that it is a value of 2 times 10 to the 4, or 20,000 newtons per meter. So K is 2 times 10 to the 4 newtons per meter. All right. We are given the recoil velocity of the carriage, which is 95 meters per second. Let me correct that. We're actually not. We are given the launch velocity of the ball, which is 95 meters per second. And we're given the angle of that launch. And we're given the weight of the carriage, so we'll go ahead and write that down as well. So the weight of, and I'll just call this the cannon, because it's the cannon plus carriage, is 45,000 newtons. Okay, so if we go ahead and divide by 9.8, we can find the actual mass, which will be more helpful. So kind of an intermediate step or immediate thing we have to calculate here. So divide by 9.8. And the only reason that we need to do that is because we're not always going to be able to just look at weight here. We're not just going to have mg in every term where we have the m. Okay, so the mass of the cannon, it will write as 4,590. And we'll use the unrounded value saved in the calculator. Right? And that's going to be in kilograms. Okay. We are also given the maximum force exerted on the carriage by the spring. All right, so F max on the spring is given as 1.88 times 10 to the 4 newtons. Okay. All right, and then now I want to get back to that velocity that we're given and draw that in our figure. All right, so let's move the ball down to here. Okay, so I'm just going to draw the velocity vector here. All right, so this is the velocity for the ball. Okay, and there's of course two components to that velocity, an x and y component. All right, so we'll call this Vx and Vy, and we also have the angle, which will just be 45 degrees because it's the same angle as shown in the figure. All right, but I'll call that theta. All right. Okay, so with our information collected, let's think about the two key steps to solving this problem. And here I'll write the value of the velocity of 95 meters per second. Okay? Okay, so the two key steps we want to consider. Okay, so step one is that momentum is conserved in the x direction, which I will show here. Okay, and that's going to be momentum conservation during the explosion, during the launch of the ball from the cannon. And one other velocity that I have not drawn here, which we'll have to solve for, is the velocity of the recoil of the cannon. All right, so I'm going to call this V, and we'll go ahead and call this cannon. All right. So cannon. All right, now our picture is complete, and we've even shown the direction of positive x. Okay. Step two of the problem is to use energy conservation, or to note that energy is conserved in the spring after the firing of the cannon. Okay, so those are our two bits of conservation: momentum and energy. Okay. And one thing to take note of here that is a subtlety of the problem is the fact that momentum is only conserved in the x direction. And that's because there is no p conservation, the p for momentum, in the y direction because of the unmovable ground. All right, so the ground is so massive that it's effectively unmovable. It would have negligible recoil velocity, so we can just not consider any conservation in that direction because of ground. All right. So it's an important thing to consider. Obviously, we could change that in the problem. We could have the cannon launch on a boat and give a certain basically elastic property to the buoyancy of the boat. You know, there's other ways that we could do this problem, but here we're just considering that it's solid ground and only conservation occurs in X. So in order to solve this problem, we have to actually want to work backwards from the second thing that's conserved, which is the energy. And the reason I say that this is working backwards is because it is really the second step, right? Momentum conservation occurs first, and then we have energy conservation, because if the cannon fires, then it recoils, stretching the spring, which causes the energy conservation. So the order is definitely set, but not the order that we solve it in. Okay, so here we're gonna work backwards from energy conservation, which is step 2. We want to consider the energy at the 2 different points, so at point 1 and point 2. Okay, and what are going to be points 1 and 2? Well, that's immediately after the firing of the cannon is energy point 1. And that's when the cannon is rolling back with its recoil velocity, so V cannon, and that has a certain amount of energy associated in it. And then we have the second point, which is after the spring is maximally compressed. So we can think then of E1 occurring right here, and then E2 occurring at maximum compression. Right, so it's going to be over here. Okay, so let's just do that. Just trying to show a dotted line to kind of show that the carriage continues to move backwards, and that's going to result in some second energy state. And it's also worth pointing out, this is energy conservation of the cannon spring system. Okay, so of the cannon spring system. Okay. All right, so what is that going to look like as we actually solve for what we want to solve for? And what is it that we want to solve for? Well, we want to solve for the recoil velocity of the cannon, because we don't know that. We know the launch velocity of the ball, which is given as 95 meters per second, but we're trying to find the mass of the ball. So if we want to, so we have 2 missing pieces of information in our momentum conservation. We don't know the recoil velocity of the cannon, although we do know its mass, and we don't know the mass of the ball. So we have to learn one of those unknowns before we can learn our second desired unknown, which is the mass of the cannonball. Okay. Okay. So I'm going to show you the algebra to solve for the recoil velocity of the cannon, or the velocity of the cannon. All right. So what that's going to look like is this right here. All right, so we're looking at the spring force, okay, which is given from Hooke's law, which is equal to kx max. Okay, so we're going to do that because we want then to put in the information that we know in terms of the maximum force, because this we are given the F spring max. And we are given k, but we're not given x max. So what I do here is I solve for x max, so I can substitute it into the conservation of energy equation, which is just the 2 states, energy 1 and energy 2. That's all we have here. It's just E1 here, and it's just E2. Okay, and so they know that they're equal to each other because that mechanical energy is conserved. If there was a non-conservative force, we could put it over here, but there's not. Okay, so then it's just a matter of solving for the velocity of the cannon, and when we do that, we find that the magnitude is given as this. Now I say it's the magnitude because we've used an energy conservation equation to find the velocity of the cannon. That doesn't tell us anything about its direction. Now we know it has to be backwards. It has to. From conservation of momentum, if the ball is moving forwards and both objects were at rest before the explosion of the gunpowder inside the cannon, then the velocity of the cannon and the carriage must be backwards. because they have the velocities, or rather the momentums in the x direction have to sum to 0 because the initial momentum in the x direction was 0. But the energy conservation gives us the momentum, which now, gives us the magnitude of the velocity of the cannon, which now we can use in step 1 to actually solve for the mass of the ball. All right, our unknown. Okay, and I've just rearranged things here to make room for our last step, which is moving on to step 1 to actually use momentum conservation. Okay, so let's talk about that step. Okay, so let's take a look at it and see how we can use the information from the first part, which is the magnitude of the recoil velocity, to solve for our unknown mass. Okay, so here we see the second step. We're going to use that value, the v cannon, to find the mass of the ball using momentum conservation. Okay, so here we just write out momentum conservation. Well, we know it starts at 0 because the system started from rest. Then afterwards we're going to have the mass of the ball and the velocity of the ball, and we're going to have the mass of the cannon and the recoil velocity of the cannon, and we know we have a known direction of the recoil velocity. Now the reason that I put this in, that I put the negative in, is because if we were, say, solving for the recoil velocity, which is perhaps a more common thing to solve for, then we would then be in a situation where the negative would occur naturally. But since we're solving for the mass of the ball, that's our unknown. We're trying to do some forensics here to find out this missing ball, how big was it? Say if it just disappeared after the firing, got lost. Well, we have to make that assumption. We have to have that negative, because otherwise, if we don't assume the negative velocity, then we're going to end up with a negative over here, which is going to give us a negative mass. Okay? So it's a known direction. We know that the cannon is moving backwards. Okay, so now let's I went ahead and did the algebra here, where I plugged in the velocity of the cannon. So we see that being inserted right over here. All right, so first of all, I just do momentum conservation to solve for the mass of the ball, just by moving things over to the left-hand side of the equation. Okay, and then the negative disappears. And then I go on to actually substitute in for the velocity of the cannon this expression right here. Okay, so that's just the force max, the mass of the cannon, and the spring constant. Notice that since I had a mass of the cannon already, and I had a mass of the cannon in the denominator inside the square root, that ends up as the mass of the cannon in the square root in the numerator, because essentially I had it to the power of 1 and to the power of negative 1/2, and 1 minus 1/2 is 1/2. So that's why we have the square root of m cannon in the numerator. Okay, so now we can go ahead and plug in our values, which I've done here. So let's open up the square root function. All right, so we're going to have 1.88 and then times 10 to the 4th. Okay, so that just being the maximum force, that's F max, which was given right here. All right, and it shows up right here and right here. Okay, and then all still within the root, we have the spring constant. Okay, this is not supposed to be inside the root, so let's get rid of that. Okay, all right, so 1.88 times 10 to the 4, and then in the denominator we have 95, so that is the velocity of the ball. But we don't just want the velocity of the ball, we want the x component of the velocity of the ball, right? Because it was always the x component of the velocity of the ball. We didn't have to worry about a component of the velocity of the cannon because the cannon was entirely in the x direction. But the ball has velocity components in both the x and the y, so we only want the x component. Well, the x component is going to be the magnitude, 95 meters per second, times cosine of 45. Now, since it's 45, we actually could have used cosine or sine, but the correct would be use cosine because it's just SOHCAHTOA, and the x component is the adjacent side of the right triangle relative to the given angle, theta. Okay, so 95 multiplied by cosine of 45. Okay, and we'll close off that denominator there, and now we multiply by the square root. Okay, and the square root, that's going to have the mass, which is up here. All right, and then that's going to be divided by the spring constant. Okay, so it's going to be divided by 2 times 10 to the fourth, but I need to put this in parentheses because we have multiplication. All right, so 2 times 10 to the fourth. Okay, close off the root. Okay, now we get 180. This is not correct because we have to change the mode of the calculator. So I'm going to change it to degree mode. Okay. All right, so now that we're in degree mode, we can go back up and make that calculation again. And we get 134 kilograms. The mass of the ball, the missing ball, and its unknown mass we have solved for using conservation of energy and conservation of momentum, and acknowledging that momentum is only conserved in the x direction, and taking the x component of the velocity of the ball, since that's the only component of its velocity that is involved in conservation. Okay, thank you.